Welcome to today's lesson. I am mwalimusamnyamu. I remind you to subscribe to the channel so that you don't miss this and other exciting videos whenever they are uploaded. In our topic today, we are going to look at metals, and basically the objectives of our lessons are as follows. By the end of the lesson, you should be able to name the chief ore of certain metals, should be able to describe and explain the general methods used in extraction of metals from their ores, select and describe suitable methods of extraction of certain metals from their ores, describe and explain physical and chemical properties of some metals, and state and explain various uses of these metals. Most metals are found combined with other elements, and only a small percentage of metals occur naturally. Examples of metals that occur naturally are arsenic, antimony, and bismuth, like you can be able to see from here. Then other category of metals are extracted from their ores. And basically when you speak about an ore is a naturally occurring solid material from which a metal or a valuable mineral can be extracted profitably. And you underline the word profitably. The chief ore is an ore from which a metal can be obtained on a commercial scale. We look at the methods of extraction, and basically we have three main methods of extracting metals from their ores. The first method is reduction of the ore with carbon. The second is reduction of the molten ore by electrolysis, and reduction of the ore with a more reactive metal. In the course of the lesson, you will understand that some metals are best extracted by one method because of a certain characteristic that we'll be able to see. That is to mean that while some metals are best extracted through electrolysis, other metals are best extracted through reduction of the ore with carbon or with a more reactive metal, like we are going to see. So we now look to understand that the process of extraction involves first concentrating the ore, and concentration is done to remove the unwanted materials. Remember that every time you are extracting an ore, we are getting a metal from its natural setting, which mostly is from the earth. And that means that the ore is usually mixed with other matters like the soil, like the sand, and many other materials. So concentration is basically done to remove all these unwanted materials so that you're left with a metal deposit that is ready to be used. This concentration is usually done by various methods, and one of the common methods is by using a magnet, where the materials or the unwanted materials are magnetic. You can also do it through hand picking, where unwanted materials is just picked from the ore. And also have froth rotation that we'll be looking into in deeper details within the course of the lesson. We have also washing with water. Some unwanted materials can actually be removed from the ore through washing with water. We look at the first metal, which is called sodium. And sodium exists in combined form, such as sodium chloride, which basically is found in dissolved form in lakes or in an ocean. If you taste the ocean water, for example, the Indian Ocean water, it tastes so salty. The main component that contributes to the saltiness of such waters is because of the dissolved sodium chloride. Another good example is the Lake Magandi. If you taste the water in Lake Magandi, where we extract the common salt from, it's so salty. The saltiness is basically because of the dissolved sodium chloride. We have also another form in which sodium exists. It is in form of trona, and trona is basically a double salt. Basically, trona is a double salt, and this double salt basically has the following formula. So that now if you want to write the formula of trona, it's basically sodium carbonate. Then we have sodium hydrogen carbonate, and then we have 10 water molecules. Basically, this is the common salt and the double salt containing more than 2 cations, and in this case, more than 2 anions, whereby we have carbonate, and it also contains hydrogen carbonate, and that constitutes what we are calling trona. Like you can see from the formula, trona contains, like you are able to see from this, you note that trona has sodium. It has sodium. Now this sodium can be extracted, and when we do that, we say that we can commonly agree that sodium or trona basically contains a lot of sodium. We also have the rock salt, and rock salt is simply solid sodium chloride, and basically this is the ore from which sodium is extracted from. And then we have the saltpeter, which is basically the solid sodium nitrate. It is also a compound that contains sodium chloride. We look at the next bit here. Let me first clear this, and then now we can look to the next bit here. Nice. We look at now extraction. And sodium is extracted through electrolysis by either Castana process or Downs process. But at our level, we will look at the Downs process, and then later in life, as you further your studies, you'll be able to look at Castana's process. So Downs process is basically can be simply illustrated like you can see in our diagram here. From here, you are able to see that yes, you are able to see that that we have an hole, and this is the hole where sodium chloride, which is now the rock salt, is fed into our cell. From here, you are able to note that we also have an anode, which is here. This is what we are calling our anode. And then we also have the cathode, and this is our cathode. There is also a cathode here. It's something that is circular. Basically, it looks like something that is circular like this, so that you can be able to note that this cathode is in contact with this other cathode. If you look at the 3D figure, you can be able to see that one very clearly. Then you also have a diaphragm. The diaphragm is what is dotted here. You can be able to see. Whatever is dotted here is what we call the diaphragm. And then we're able to see that we have an outlet. and then we also have another outlet. So basically we have one inlet and then we have two outlets. One is for the chlorine gas and the second one is for sodium metal after electrolysis in Downs process. Sodium and chlorine are basically prevented from recombining by the diaphragm. So the purpose of the diaphragm that we just saw is for the purpose of preventing chlorine and liquid sodium from recombining. The Downs cell is made up of iron shell lined with heat bricks. So what you are seeing is just lined with the heat bricks that maintain high temperatures inside the cell. Because remember, sodium has a very high melting point, and for that purpose we need to have a lot of heat. And one of the ways to maintain the high temperatures in our cell is by lining the walls of the cell with heat bricks, so that now the sodium chloride remains in molten state throughout the process. And we add sodium chloride. Sodium chloride is basically added together with sodium chloride. As you add sodium chloride in the down cell, it is mixed first with calcium chloride. And the purpose as to why, or the reason as to why we have this what we are calling calcium chloride. Calcium chloride lowers the temperature of sodium chloride, that is the rock salt, from 800 degrees Celsius to 600 degrees Celsius, which is very economical because the electricity that is required to obtain these temperatures is quite high. Then we now look, during electrolysis, sodium ions will migrate to the cathode where sodium metal forms, while the chloride ions move to the anode where chlorine gas forms. We look at the equation at the anode. At the anode, this is where we have the anode. Just a moment, just a minute. So we have what we call our anode here, where we have this anode. This is where, remember that the anode is positively charged, and at the anode you expect that the chloride ions from the rock salt will be attracted towards this anode, while the positively charged sodium ions will be attracted to this cathode, because the basic law of charges states that the like charges repel while unlike charges attract. So the charges on this cathode are negative, and therefore you expect that sodium, which is positive, the sodium ions which are positively charged, will be attracted towards this. And basically that is also, let's just look at the equations at both the anode and the equations at the cathode. And we begin with the equation at the anode. Like you can see here, we have, like you're able to see here, what we have is basically the chloride ions at the anode. Anode is usually positively charged, and therefore you expect that the chloride ions which are negatively charged will be attracted to it. So by this, the chloride ions, they lose electrons, and the electrons that are lost are the ones that you see here, 2 electrons. The 2 electrons are coming from 2 chloride ions. So each chloride ion releases or loses 1 electron, and because now we have 2 of them, they lose 2 electrons with formation of chlorine gas. So from 2 chlorine atoms, we have a molecule of chlorine which is made up of those 2 chlorine atoms. When that is done, we also look at the equation at the cathode. So the 2 electrons that are lost by chlorine are now attracted by sodium. These are the 2 electrons. So sodium, what sodium will do, sodium ions will gain the 2 electrons. So each electron per sodium atom to give us sodium atom. And you need to note that here in this case, it is in liquid form. This is because the temperatures still are very high in the down cell that make sodium to basically remain in molten state. We now look at what we have here. After reduction of sodium ions to sodium atom and the oxidation of chloride ions to chlorine gas, how now do we end up having sodium? So we are saying that the less dense sodium metal floats on the molten sodium chloride and is periodically removed. How is it periodically removed? We are saying that sodium is less dense, and for that reason, when it is dense, we expect that it will float. Remember, this is just a space where this is a space that is occupied by sodium chloride. So once sodium is reduced here on these cathodes, it ends up floating on the sodium chloride, and therefore it is tapped periodically and it gets out through that outlet that, like we had mentioned in our previous slide. And then from this we get to look at now another point here on chlorine produced is not released to the atmosphere as it is a poisonous gas. Chlorine is a very useful gas. It has a number of uses, and therefore we don't, for being useful and also poisonous at the same time, we don't release it to the atmosphere, because once released to the atmosphere, of course, inhaled by human beings or any other living thing, it causes a lot of filtration, and for that purpose it is not released to the atmosphere. And again, it is tapped and reused because it is a very useful gas, for example, in the manufacture of Zinc, in the manufacture of the CFCs, and many other uses, the polyvinyl chloride, and so on and so forth. We do not release chlorine gas to the atmosphere. We also have calcium. Remember, we said that we add calcium chloride to the sodium chloride, which is the rock salt, to reduce or to minimize the melting point from 800 to around 600 degrees Celsius. So for that reason, calcium also is reduced at the cathode. And we need to ask ourselves, how can we now be able to separate? You might need to know how to you end up separating sodium and calcium, which have been tapped together at the cathode. And this one is very simple, simply because calcium has a much higher melting point compared to sodium. And for that reason, when you subject them, when you no longer subject them to heat now, as they cool, calcium cools fast and solidifies, leaving sodium as a liquid, and therefore it can be removed, and then we'll be left with liquid sodium, which later solidifies, and then now we'll be having our sodium extracted. On the uses of sodium, I encourage my students that you do a research to be able to mention at least, I advise for you to at least be able to mention like 5 uses of sodium. We look at the next metal, which is aluminium. And aluminium exists in combined form, such as bauxite, which is that formula, the formula that you're able to see here. And remember that bauxite again it is the chief ore. We said that a chief ore is an ore from which a metal can be extracted, from which metal is basically extracted from. So we extract aluminium from bauxite, while mica is another ore of aluminium, but not very popular in extraction of aluminium, as well as corundum. Aluminium is a very useful metal. It is used in making of the utensils because of a number of properties. For example, ability not to rust like iron does or corrode easily, and also the aluminium sheets. They are also very, very, very good quality compared to the iron sheets, so that we can summatively agree that the iron is actually being replaced by aluminium in the manufacture of the roofing sheets. And we might need to know how aluminium is extracted. And number one, being a very reactive metal like sodium, it is also extracted through electrolytic method. And this is basically the use of electrolysis to decompose the compounds from aluminium so that we are left with pure aluminium. And aluminium ore contains both iron 3 oxide and silica as the impurities, and therefore means that as we try to extract, we will be keen to check how we will be able to get rid of these two impurities. And number one, the ore is concentrated. Recall we said that concentration simply implies removing the unwanted materials before extraction. And the concentration of aluminium involves grinding bauxite into a fine powder. After grinding, it is then dissolved in hot concentrated sodium hydroxide under pressure. And then aluminium oxide now and silica 4 oxide dissolves in the base, while the insoluble iron 3 oxide filters out as mud. What does that mean? That means that the first impurity, which is iron 3 oxide, is got rid by dissolving concentrated sodium hydroxide into our ore, whereby now the first impurity, which is silicon 4 oxide, and the aluminium oxide, which is the main component in bauxite, dissolves, leaving the insoluble iron 3 oxide, which is now filtered out as mud. And therefore, we can have an equation for that links to the formation of how now the concentrated sodium hydroxide dissolves aluminium 3 oxide and silica. And like you can see here, we have what we have here as aluminium, then the hydroxide ions from the sodium hydroxide in presence of water gives us this complex of aluminium. And then we also have for silica plus hydroxide, which gives us this compound of silicon. And from this, we can now get to the number 4 after decomposing. Remember that we're in the process of extraction. And number 4 is we bubble carbon 4 oxide through the filtrate. Remember that our filtrate here is the aluminium compound that we saw. It is this aluminium compound. It is this aluminium compound and this one that makes up the filtrate. So what we do, we do what? We do this. We bubble carbon 4 oxide gas through the filtrate, and aluminium hydroxide precipitates out according to the following equation. The equation is already here. What we have is the compound, the aluminium complex, reacting with now the carbon 4 oxide that we just bubbled. It gives us aluminium hydroxide. We have carbonate ions, and the water is also formed. And in this case, you might need, there is like you can see here, we have that arrow. It is wrongly placed. It is supposed to be here. Let me just write it with a color that is much visible. It's supposed to be here, so it forms what we have there. Good. Now we have separated all the impurities from our main component that we want now, which is the aluminium oxide, which later was formed the aluminium hydroxide. And now the aluminium hydroxide, from the aluminium hydroxide, now we need to look at the next step. And what is that next step? That is now what we call the electrolysis extraction, electrolytic extraction of aluminium. It is taken into this kind of cell whereby we have two electrons, and these electrons are positively charged, like you can see here, and that means that these are two anodes. And then we have a cathode, which goes around the container like this. So the whole container is surrounded by the cathode. We also have what we have as an information we need to note is that the cathode is made up of carbon. All right? The anode as well is made up of what? Carbon. So we need to look at what happens at the anode. So taking this as our anode, remember we are now having molten aluminium oxide. So we expect that at the anode, the aluminium ions will not be attracted there. But then the oxygen ions from aluminium oxide will be attracted there. After attraction, the oxygen ions lose electrons. This is what we are calling the loss of electrons. And when they do so, they form oxygen gas. This oxygen gas, these are atoms, they do combine to give us the molecules of what? Oxygen gas. So these are atoms combining, 6 oxygen atoms combining to form 3 oxygen molecules. From here, we need to know that the oxygen produced at the anode reacts with the carbon, and hence the carbon electrons have to be replaced periodically. We're saying that the electrons in this case, and these are the electrons that we're speaking about, these electrons are made up of carbon. And for that reason, they react with the oxygen that is produced here when oxygen atoms are oxidized to oxygen atoms. And the result is formation of oxygen gas. So this oxygen gas reacts with the carbon electrons to form carbon dioxide, and for that purpose, the electrons have to be replaced periodically. Now look at the equation at the cathode. And at the cathode is here. This is what we call the cathode. The cathode is negatively charged, and therefore you expect the aluminium ions to be attracted or to migrate towards it, because the unlike charges always do what? Attract. So at the cathode, aluminium ions, they gain the electrons lost. So we can unanimously agree that this is a gain of electrons to give us, this is 4 aluminium, and the state is sorry, the state is not solid. The state is liquid because it is in molten state, and therefore that is what happens at the cathode. We now look at the next metal, which is called iron. And iron is very useful. Iron has a number of uses. You have, at any given point, you have ever used a spoon. You have ever seen the material, the metallic material that is used in making of mostly the windows, the doors, or even the iron sheets. And that means that at any given point, or you've ever seen a knife written stainless steel, that is just an alloy, or it's just a form of iron. And therefore, iron is a very important metal that you need maybe to look at how it is extracted. And to begin, we look at the ores of iron. We need to know how, or from what ore is iron extracted. And the first ore is hematite. Hematite is simply iron 3 oxide with this formula. And this is the chief ore. This is the ore from which iron is extracted. We also have magnetite, which is this, iron 4 oxide. And we also have the siderite, which is basically iron carbonate. The last two, these last two, basically these last two, these last two what? These last two ores, we are saying that this, sorry for that, these last two ores are not very popular in the extraction of iron. So we mostly extract iron from the first ore, which is hematite. The impurities are silica with this formula, and we also have aluminium oxide. And we now look at extraction. And in extraction, we say that we say that iron is usually extracted from its oxide when siderite is used. Remember the formula of siderite? This is the formula of siderite, iron carbonate. The ore is first roasted in air to convert it into iron 2 oxide through thermal decomposition. So we have kind of an arrow here. So iron carbonate, this is done through heating to give us iron oxide, iron 2 oxide and carbon 4 oxide. The iron 2 oxide is then further oxidized to iron 3 oxide by oxidation by the oxygen in air. And this is basically the equation. This is the equation that leads to that oxidation. And from this, what we need also to now to look at is how iron is extracted and by which method. And in this case, we say that iron is extracted in a blast furnace. And the blast furnace is simply it's simply a place where there is it's like it's a furnace that is lined with bricks. So whatever you see here, these are just bricks, and the purpose of these bricks is to ensure that the heat that is supplied to the blast furnace does not get lost, or it ensures that there is maintenance of very high temperatures, and these temperatures are the ones that do what is called smelting, which is simply converting a metallic solid into a liquid state or molten state. So this is a blast furnace. Like you can see, we have where we have the iron. You see here? Let me just change the color so that it's a bit visible. Let me use red. Yes, here we have iron ore, we have coke, and we have limestone. Remember that coke is basically impure form of carbon, and limestone is calcium carbonate, both impure. So they are fed together with the iron ore, which is now iron oxide from the top. After being added there, you note that there is a blast. Look here, we have a blast of air, and not just air, but it is hot air getting in that is hitting our raw materials, which is iron ore, the coke, and limestone, the ones that we have here. You also need to note that we have different temperatures at any given level. Remember that the height of these furnace goes up to that meter, so it's not something that is very short. So there is what we are having now as 1500 degrees Celsius. We have 850 degrees Celsius, 700 degrees Celsius, and 250. And basically cooling takes place normally because at the bottom is where the blast of air is, and the air is the one that is hot. And as we go up, you expect that the substances get cooled. So from this, we will look at the next page, and we'll see that iron 3 oxide is first ground and mixed with limestone and coke. We have already mentioned that, and it is fed into the furnace from the top, where it is heated by blast of air from the bottom. So this is the bottom from where we are saying that this is the bottom. This is the bottom that we are saying that the materials, these materials are burned from the bottom by this blast of hot air. At the bottom, this is the equation that happens. We say that the coke burns in the blast of hot air to form carbon 4 oxide. So the coke, which we said is basically impure carbon, is the one that burns at the bottom to give us carbon 4 oxide, like you can see here. And this reaction is exothermic, and therefore the temperatures go up to 1600 degrees Celsius. So we can say that the burning of coke actually raises the temperatures to about 1600 degrees Celsius. And when this is done, at the middle, so we agree that at the bottom we have carbon being reacted with oxygen to give us carbon 4 oxide. And then now at the middle is where the temperatures are around, at the middle is here. I can just show you. At the middle is around this space here. See this space? Yes, that is what we call at the middle. And we're saying that at the middle, the carbon 4 oxide reacts with carbon to produce carbon 2 oxide. This is a reduction reaction, whereby now the carbon 4 oxide that is produced at the bottom reacts with carbon to give us carbon 2 oxide. We're saying that this reaction is endothermic. It takes heat from the environment, it takes heat from the surrounding, and this lowers the temperatures to 1000 degrees Celsius. And then we have at the upper region now, both carbon and carbon 2 oxide reduce iron 3 oxide into iron metal. So note these 3 equations. We have at the bottom where coke burns in oxygen to give us carbon 4 oxide. We're saying that that reaction is very exothermic, so it raises the temperatures to around 1600 degrees Celsius. Then at the middle, we have now the carbon 4 oxide produced reacting with carbon to form carbon 2 oxide. And you're saying that this reaction is endothermic, and it lowers the temperature to around 100 degrees Celsius. Then we have the upper region. This is where now we have iron. Okay? And this iron is now reduced by both carbon 2 oxide and what? And carbon. And it is reduced to what? It is reduced to iron metal. And these are the equations. We have iron 3 oxide, this is it, reacting with carbon to give us iron plus carbon 4 oxide. If you look at the next equation, we have iron 3 oxide again reacting now with carbon 2 oxide to give us iron metal and carbon 4 oxide. In both cases, we have production of iron metal. Okay? We need to ask ourselves what is the purpose of limestone, because we haven't seen the purpose of the limestone so far. Limestone is basically decomposed by the heat in the furnace to form calcium oxide and carbon 4 oxide according to this equation like you can see here. So this calcium oxide, remember it is basic, okay? It reacts with the acidic, we are saying that calcium oxide will react now with the acidic and amphoteric oxide in the furnace to form slag. Now, being basic, what is this acidic compound that you have and the amphoteric oxide that you have in the furnace? Recall the impurities. So this is it, the silica impurity that we mentioned. Reacts now with calcium oxide to form calcium silicate. The calcium oxide also reacts with aluminium 3 oxide to give us calcium aluminium oxide. All right? Aluminium silicate. This, I think it's the name of this one is aluminium silicate. And then these are now our impurities. The two impurities have been reduced through what? By what? By our calcium oxide. So they separate out as slag. And you're saying that the slag being less dense, it's less dense than iron. It floats on it and is tapped off. And iron obtained by this way, we say it is called pig iron, and it is about 95% pure. The impurities in it can be carbon, the silicon, manganese, sulfur, and phosphorus. They make iron less hard and lower its melting point. I will take you back to a blast furnace so that we see that where we need to look at where the molten iron is getting out from. So we have iron getting out through this outlet, and we are saying that the slag, which is less dense, floats on this iron and gets out through this second outlet. And having said that, we now get to the next metal, which is called zinc. So basically, zinc is also a very useful metal, and the ores of zinc include calamine, which is basically zinc carbonate, which is actually the chief ore. We have also zinc blende. Zinc blende is basically zinc sulfide, which is also a chief ore. And then we also have galena. Galena is lead sulfide, usually found combined in zinc blende. So anytime we have zinc blende, it is very likely that we will also find galena combined in it. We look at extraction. Extraction number 1 process is concentration of the oil through froth flotation. And then from there, the oil is then ground and kept in large tanks containing water and pine oil. This is actually now the froth flotation. And the mixture is agitated by passing compressed air. All forms froth. The froth now comes at the top. It's something that forms at the top, like we see the what? How do we call the form of a soap forming at the top of the water when it is agitated, and comes at the surface where the impurities are left in the water. And from this, what we do, we now take our calamine. Remember that calamine we said is zinc carbonate. It is decomposed through heating to give a zinc oxide and carbon 4 oxide. And in case we are using zinc blende, we send it zinc sulfide. You need not to forget the formula of these oils. We decompose it on heating as well to give a zinc oxide and sulfur 4 oxide. And remember that our interest here, the interest always is where we have zinc. And the impurity galena is also roast to produce. Maybe we say that in every time we have zinc blende, it is very likely that we also find galena mixed, and galena is basically lead sulfide. On roasting it, it gives us also lead oxide and sulfur 4 oxide. So we have zinc, which now is combined with oxygen. How do we separate it? We say that this zinc can be separated from oxygen by reduction by carbon 2 oxide. The next method, or another option, is by electrolyzing it. But then for electrolysis, you need first to convert it from zinc oxide to zinc sulfate by reacting with sulfuric 6 acid. So extraction by electrolysis, main methods of extraction, which is actually the main method of extraction, the zinc sulfate is then dissolved in water and the solution is electrolyzed. The cathode is made of pure zinc or lead containing 1% of silver, while the anode is made of aluminium sheets. At the anode, both hydroxide and the sulfate migrate to the anode. But then in this case, the hydroxide ions are the ones that are preferentially discharged. They are preferentially discharged. That means that the sulfate ions are not discharged to give us water, oxygen, and a few electrons. That is 4 electrons according to this equation. Then from this, we need to look at what happens at the cathode. And at the cathode, both the zinc and hydrogen ions migrate to the cathode, but zinc ions are preferentially discharged. And we can see and look at this equation where we have zinc ions migrating to the cathode, and they are reacting now with the 4 electrons, gaining of electrons, to form zinc solid. This reaction is basically reduction of zinc ions to zinc metal. And we might need to ask ourselves, why do we have why we don't use the graphite electrons? And in this case, we are saying that graphite electrons are used in hydrogen. Then hydrogen would be preferentially discharged. So for that reason, we don't use the graphite electrons. Otherwise, hydrogen would have been preferentially discharged. We look at the next method through which we can be able to obtain our zinc, and this is reduction by carbon and carbon to oxide. If we look at this setup, you note that we have hot zinc oxide and coke getting in through this topmost part here, and then we are having it get into the bottom, and then after it gets to the bottom, we have this hot blast of air, hot blast of air. And from this, what happens? The zinc oxide together with coke are heated, and what we see here is zinc vapor, which now gets in here and gets cooled back into a liquid, which further becomes a solid. So the question is, how are we able to get zinc vapor by this method? And we look at it from the second or the next slide. At the furnace, zinc oxide is mixed with limestone and coke, calcium carbonate, and coke, heated and reduced to zinc metal. So once we heat them, the zinc oxide is reduced by carbon to zinc and carbon to oxide. The zinc oxide also reacts with the carbon 2 oxide produced to give us zinc and carbon 4 oxide. You note that the zinc produced is in gaseous state. This simply because the temperatures at the furnace are very high. They convert the solid zinc into liquid state. So limestone decomposes on heating to form calcium oxide and carbon 4 oxide. And then the carbon 4 oxide is then reduced by coke to give us carbon 2 oxide. So the main or the two reducing agents in this type of furnace is number 1, coke, and also carbon 2 oxide. The equation resulting from the decomposition of limestone, it's calcium carbonate. Remember saying that limestone is basically calcium carbonate. On heat, it is decomposed to calcium oxide plus carbon 4 oxide according to this equation. Well, now, the carbon 4 oxide from limestone reacts with carbon. The carbon, remember, it is the coke that we supplied together to give us carbon 2 oxide. And what is the purpose of this carbon 2 oxide? The purpose of carbon 2 oxide, it will be to reduce the zinc oxide to zinc metal with formation of carbon 4 oxide. And we need to know that the furnace temperatures are maintained above 1000 degrees Celsius because the melting point of zinc is a bit lower, which is 913 degrees Celsius. That means that if that is the melting point, zinc vaporizes and leaves to the top of the furnace together with the other gases. Which other gases? Carbon 4 oxide and carbon 2 oxide. So this zinc vapor is then cooled by mixing it with a spray of molten lead at 600 degrees Celsius. This is where the spraying takes place. The spraying takes place here. It takes place here, which now converts the vapor, which converts now the zinc vapor back into liquid. And after that, we are saying that the spray condenses zinc and prevents it from being reoxidized back to zinc oxide, and the zinc obtained this way can be purified by distillation because it contains the lead vapor. Sorry, the zinc. Sorry, I'm saying that the lead obtained this way can be. What am I saying? Sorry. I'm saying that the zinc obtained this way can be purified by distillation. Okay, yeah, this is to separate it now from the molten, from the zinc, from the spray of lead, like we're saying. On the uses, I will not also mention the uses of zinc. I advise that you get deep into your notes and look at that. So in our next lesson, we shall be looking at lead, extraction of lead, the extraction of copper, and that will mark the end of our lesson. So I advise that you watch the next video on extraction of lead and extraction of copper. Thank you for watching. Subscribe to the channel so that you don't miss and these other exciting videos. I am mwalimusamnyamu, your chemistry and physics teacher.